Hello and welcome to the Glacier Pavilion. My name is Thomas Frank and I'm a PhD candidate at Uppsala University in Sweden. We're today focusing on the two big ice sheets in Greenland and Antarctica, and we're starting off the day with a session on West Antarctica, Getz on the Run. I also wanted to welcome those of you watching online in our hubs in Geneva and Stockholm. And if you have any questions there, please feel free to type in the chat. For those of you attending here, you can ask questions after the event. I would now like to introduce Heather Selley and Bryony, our two speakers today. Heather Selley is from the University of Leeds, and Bryony is from the University of Leeds and the British Antarctic Survey. Heather, the floor is yours.
So hopefully this level of sound is okay. Thumbs up, that's great. Hello, thank you for coming along today, and thank you to the ITC for organising the Cryosphere Pavilion. First of all, just introduce myself. I'm Heather Selley. I'm a PhD researcher at the University of Leeds. And the way the session is going to work today is Bryony and myself are going to switch off. Bryony is also a PhD researcher. So we've got 4 sections. So the first section, we're going to be talking to you about the importance of the Antarctic ice sheet. And then we're going to be talking to you about why satellite data is so amazing and a vital resource in understanding the Antarctic ice sheet. Then we're going to give you a little case study of the Getz region, the namesake of this presentation, which shows the use of satellite data and ice sheet modelling and how beneficial it is to use these in combination. And then we're going to finish off by talking about the naming of glaciers. You may have seen in the news last week, Glasgow Glacier was named, and I was the person that put in that proposal. So hopefully you'll indulge us as we go through the reasoning behind that. We wanted to highlight, as early career researchers, that the mid-career and senior career women that paved the way for us to be here, but we also wanted to highlight that there's still a lot of groups that experience discrimination, especially with those with intersectional characteristics. And it's really vital that we have diverse backgrounds, perspectives, experiences coming together to try and create innovative and creative solutions to problems. And our generations are facing the largest problem that we've ever seen, which is the climate crisis. So it works great. So we'll start with the importance of the Antarctic ice sheet. Back in the 90s, the ice sheets only contributed about 5% to global sea level budgets. That's increased 5 to 6 times up to present day. In this graph, you're seeing the contributions of Greenland, the Northern Hemisphere ice sheet, and Antarctica, the Southern Hemisphere ice sheet. And the blue line is the combination of these contributions. That data is based on satellite observations. The red, orange, and peach line that are appearing are the Intergovernmental Panel on Climate Change, 5th report's projections of global sea level. And as you can see, the blue line is tracking closest to the red line. Closest to the red line. Now, this is important because at the moment on current trajectories, we're looking at 400 million people at risk of annual flooding by 2100. And importantly, Antarctica is the largest uncertainty in our sea level rise budget. And these ice sheets are no longer the slumbering giant that we thought they were. So what are ice sheets? They're the largest reservoirs of fresh water on our planet. Antarctica is in the southern hemisphere, and it's made up of several parts. So there's the East Antarctic ice sheet, which can be up to 4 kilometers thick, and you'll see it identified with this pink line. And this map is an image of the bedrock beneath the ice sheet. So if we get rid of the ice sheet, this is what's underneath. And you'll see these red and yellow areas are where it's above sea level. And in human timescales, the majority of East Antarctica, we think, is pretty stable. However, its neighbour, the West Antarctic ice sheet, is where a lot of our research is concentrated. This is because the majority of the West Antarctic ice sheet is grounded below sea level, up to 2.5 kilometres in places. So you see this dark blue area is basically a bowl under this ice sheet. And that means as you go further inland, you get deeper and further below sea level. This means that this area is susceptible to imbalance and instability. So what makes up an ice sheet? So this is Antarctica. We have glaciers that flow around the edge out of the ice sheet. We have the grounded ice itself, and when we say grounded, that means it's sitting on the bedrock beneath. And then it transitions into these floating ice shelves that sit on the surface of the ocean. And ice shelves are important because they fringe about 3/4 of the Antarctic ice sheet. And importantly, they have a buttressing effect. And that means that they're exerting pressure inwards, holding back a lot of the ice that's grounded behind. So if you think of a champagne bottle, if you pop the cork, the champagne comes flying out because there's a release of pressure. So the cork is the ice shelves, the champagne is the ice sheet. If we lose the ice shelves, then we'll see runaway speed up and more ice entering our oceans. And this is important because the amount we warm our climate increases the susceptibility of ice shelves to collapse. So we see at a 4-degree warming scenario, they're twice as susceptible to collapse compared to a 2-degree scenario. The ice interacts with the atmosphere. So you can see over the West Antarctic ice sheet, this dark red area, which is warming faster than the rest of Antarctica. So it's driving melt from above. But it also interacts with the ocean. So these floating ice shelves, the ocean comes up underneath and melts it from below as well. And interestingly, the changes in the ocean aren't uniform, and we see the changes that we're seeing aren't evenly distributed in space and time, so they're variable, so neighbouring glaciers can have different reactions. An important area that we're looking at is the grounding line, and this is the point where the ice shelf meets the ground, the grounded ice sheet. And I'm just going to introduce this idea of these instabilities. So there's been evidence of marine ice sheet instability in paleo records, but we're also seeing some warning signals coming through now. And this is a theory whereby the hot water comes onto the continental shelf, it gets under the ice shelf and melts it from below. And much of West Antarctica is on that retrograde slope, so it's sloping downwards as you head inland. So as the water melts, there's a taller cliff underneath the ice shelf, so there's more ice exposed, which then means it melts faster, and then we kind of get this runaway retreat in this area. There's a second theory, and there's less evidence for this yet, but it's something to be aware of, called marine ice cliff instability. So this is thought to come in when if we lose the ice shelves. So you may have seen pictures of icebergs in the news, and often it's just through a natural calving cycle. However, if we lose the ice shelves, then the ice that's then at the ice front is grounded, and it's this really thick ice, and we get these really tall cliffs, which make them less stable. And then they're more susceptible to calve, and once they've calved once, we then end up with another taller cliff as it's getting thicker as we move inland, and then it's more likely to calve again having this kind of runaway effect. And the reason I'm highlighting this to you is because these are the IPCC's projections of sea level change up to 2100. So blue being the lowest emission scenario, dark red being the upper. But you'll notice this dotted red line, and that's including the instabilities that I've just talked about. And that's quite important because it changes it from a 1 meter increase, doubling it to almost a 2 meter increase. And for context, if we're looking at 2 meters by 2100, that's over 600 million people inundated with water through flooding. I think it's also important to highlight that sea level change doesn't happen evenly across the whole world. So if we say there's an average of 1 meter sea level rise, it's important we know where that water has come from. So if the majority of the water comes from the Greenland ice sheet, what you're seeing is like the ratio of the amount of sea level rise. We'll see, say we get 1 meter, we'll see 1.4 meters in the southern hemisphere near South America, but we'll actually see a drop in sea levels in the northern hemisphere around Greenland, and that includes the UK where we are today. But if it's from West Antarctica, then we kind of see the reverse. We see these higher sea levels occurring up in the northern hemisphere, and this is because if we lose these masses of ice, they're absolutely huge. So they have their own gravitational pull, and when you lose that ice, there's that changes, and then also there's some uplift of the bedrock beneath because there's no longer that ice pressing it down. So it's important we know where the water is coming from to help us project into the future the changes in the sea levels, so then we can protect the most vulnerable coastal communities and we can look at that distribution. And I've highlighted sea level rise, but there's a lot of other things that impact if we get a lot more meltwater. So we get a freshening of the ocean, which then changes the salinity or how salty the ocean is, which then affects ocean circulation patterns, which then affects atmospheric changes and also weather. But there's other things such as the fresh water increasing phytoplankton, which then affects the whole food web. So I think you'll hear a lot at COP26 that the climate is all interweaved and that every part of it is important. I think one more thing that's important to highlight is that with the instabilities that I mentioned, so this marine ice sheet and marine ice cliff instabilities, once they kick in, we think they're pretty irreversible on human timescales. So it's really important that we try and limit the warming so that we don't see these thresholds crossed and kick in, and then we can't change it. Whilst we are tied into some sea level rise because of how we've warmed the atmosphere, the oceans respond a bit slower, so they warm more slowly. So we are locked into some sea level rise, but the rates that we're seeing have increased, and it's important we bring that rate down so that we can adapt and have time to do that rather than basically creating disaster and chaos scenario. And now I'm going to hand over to Bryony, who is going to talk to you about how we study Antarctica from over 16,000 kilometres away here in the UK.
Thank you, Heather. So yes, my name's Bryony and I'm also a PhD researcher at the British Antarctic Survey and the University of Leeds. And I'm just going to be talking a little bit today about the development of satellite technology, and in particular Earth observation satellites, and how they've changed, they've revolutionized the way that we can study climate change, and in particular its impact on the Antarctic ice sheet. Now, Heather and I both use satellite data in our research, and we're going to touch a bit on what we do later. But firstly, I thought I'd take you back to the first ever Earth observation we really had, with this beautiful image of the Earthrise image taken by the Apollo 8 astronauts in 1968. Now, as well as this being one of the most stunning photos I think I've ever seen, it kind of brings important context to what I'm talking about today. Firstly, it gives us a bit of a time scale of when we have information from space as a vantage point of Earth. So we have about 50 years of this kind of information, which means we can look at changes that are happening on Earth on decadal, annual, seasonal, and even daily timescales. But we can't look back much further than this at centuries, millennia. We have to rely on other information there. Secondly, it just kind of shows the simplicity of really what we're dealing with. When we talk about satellites, it can all seem quite technical, but ultimately all we're doing is looking at the Earth from space. So at the beginning of the 1970s, it saw the launch of the Landsat mission, the Landsat program by NASA and the USGS. And this was really a significant moment in the story of this development of satellites for Earth observation. It was the first program that was designed primarily to look at changes of the Earth's landmass. And Landsat 1 was the first that launched, which has an instrument on board that measures the surface of the Earth in the visible and thermal parts of the electromagnetic spectrum. And it's been followed up by a series of Landsat missions since that ended up with Landsat 9 that got launched earlier this year. And this has provided us with a 50-year historical archive of changes on the Earth's surface that we can use as a baseline against which to measure change that has happened as a result of climate warming. So from them, we've kind of had increasing numbers of instruments put up on satellites that have different types of sensors. And an example of this has been the passive microwave sensor that's been invaluable in tracking sea ice extent and changes in this in both the Arctic and the Antarctic. This sensor can see through clouds and it can see through polar darkness. And this has allowed us to obtain information about sea ice extent and concentration on an almost daily timescale since 1978, which is pretty remarkable, I think. And this is the longest environmental data set that we have from satellites that's unbroken on record. And the important point of this is that it's records that are continuous and consistent data from satellites against which that we can measure changes that have happened with the warming climate. And the impact is no starker than what we've seen with the decline in Arctic sea ice volume in the last 40 years. And so today we now have over 650 Earth observation satellites in orbit. This is just some of them from the European Space Agency fleet that provide us information for science, operational monitoring, and weather forecasting, among other things. We also have satellites from a series of other national space programs, a lot of which the data has become freely available for everyone to use. And there's also been a big growth in the commercial sector with companies like Planet producing very high resolution information that is available at a cost, but it's a big booming industry. And as you can probably imagine, this has revolutionized the way we've studied the polar regions. They're such vast areas and often very inaccessible, remote, and very cold. So they've allowed us to collect data on these continental scales. And I'm just going to highlight some of the interesting science, and particularly with looking at changes to the Antarctic ice sheet that we've been able to obtain with satellite data. So the first example is how we can look at the extent of surface melt lakes like these, which form on the surface of the ice sheet and ice shelves every summer, also sometimes worryingly in winter as well now. And we can get images like this from the European Space Agency's Sentinel-2 satellite. This is over the George VI ice shelf and was taken at the time of a 32-year record melt event. That was reported by Ali Banwell and others in January 2020, so not too long ago. And you can kind of get an idea of the scale of these features. The two largest lakes that are in this satellite image are over 5 kilometers wide each, kind of highlighting the real value that we have in the satellite data sets for tracking these. And surface meltwater production is predicted to double by 2050. And so kind of tracking the extent and location of lakes like this is going to become ever more important, and satellites are going to be a vital tool to be able to do this. They're important because it gives us information about where temperatures are rising above 0 degrees. And also they've been linked to the breakup of ice shelves, like we saw with the Larsen B ice shelf in 2002. Now, again, we have a time lapse of imagery that should play now, of this catastrophic breakup event that happened of this ice shelf. Over the course of a single month, the satellite images show over 3,000 square kilometers of ice breaking up. And this is double the size of Greater London, to give an idea of the scale. It's a scale that had never been seen before. And it followed a series of warm summers that kind of led to a lot of surface melt happening. And you can see in these blue patches here are the surface melt lakes. And they act as wedges, kind of deepening the crevasses and causing the ice shelf to splinter. And the ice that we're losing to the ocean as part of this collapse doesn't contribute directly to sea level rise. But what we are able to measure with satellites is that all of these glaciers onto the left that were feeding the ice shelf suddenly sped up dramatically after this breakup by over 300%. And this led to a 10-fold increase in the total mass of ice being lost into the ocean every year. So this gives us a great example of how satellites can be used as an early warning system to detect rapid changes like this in the remotest parts of the world. In the 90s, the general consensus among IPCC scientists was that the Antarctic ice sheet changed on the timescales of tens of thousands of years. So it was nothing that we had to worry about. But events like this really changed our perspective on this and was a wake-up call that we really needed to pay attention to the changes that were going on here. So with satellites, we're also able to get this continental scale picture of the speed of ice. And this map just shows just that. So the pink and the blue areas show the fast moving areas of ice, so the glaciers and the ice streams that are draining ice from the center of the continent out into the ocean. And if we look at how this changes over time, we can see it can be an early warning sign of any instabilities. So all glaciers in the Amundsen Sea, which is this area to the west, we've got Pine Island and Thwaites that you may have heard about. These have all sped up since the 1990s. And this kind of speed up is happening alongside a surface lowering and grounding line retreat. And so if we're going to understand the relationship between ice loss from the ice sheets and sea level rise, we not only need to know how fast the ice is moving, but how thick the ice is there and how this is changing. So for this, we turn to another fleet of satellites known as altimeters. And this is NASA's ISAT-2, an example of one of the satellite altimeters that we have up in space at the moment. And it works by sending lasers down to Earth and measuring the surface height within 4 millimeters of accuracy, which I think is pretty staggering considering this is 481 kilometers above Earth. And if we measure surface height over the whole continent, from this we can infer ice thickness. And if we do this over time, we can see where the ice is thickening and thinning, and produce maps kind of like this from Ben Smith and others, which is showing the mass loss from Antarctica from 2003 to 2019. And it's showing us the fingerprints of two main climatic processes. So firstly, all of these red and purple regions around the margins and in West Antarctica are where we're losing a lot of ice thickness, up to 10 meters per year in some of these regions. And this has kind of been mainly driven by ocean warming and by the breakup of ice shelves like we saw with Larsen B. Elsewhere, we see a lot of blue, which is actually showing a slight increase in ice thickness. And this has been driven by kind of changes in atmospheric circulation patterns that have increased snow accumulation in these regions. And in addition to the ISAT-2 satellite from NASA, we have Cryosat-2, which is the European Space Agency's altimeter up in space. And together, these are really complementary missions, and they've revolutionized the way that we understand ice volume and changing ice loss from Antarctica. And as Heather said, the future ice loss from Antarctica is our greatest uncertainty in our future predictions of sea level change. So these are really, really important satellites to help us understand that change. They've been able to help us put the loss of ice from Antarctica in the context of global ice loss from all of these other sources, so from sea ice and breaking down the ice shelves and the Greenland ice sheet as well. But there's a big worry in the community at the moment because we're facing an imminent risk of a gap in this polar altimetry record. So as I said before, we have Cryosat-2 and ISAT-2. And the worry is these are both going to be decommissioned before we have any follow-up mission in place. Cryosat-2 was launched in 2010 and is already well outperforming its expected design life. Engineers hope that it can kind of stay working until 2024, maybe a little bit later. And ISAT-2 will, because it was launched much later, is hopefully going to last a little bit longer. But the next follow-up mission that we have on the horizon is the Crystal mission from the European Space Agency. And the funding isn't yet fully in place for this, but the earliest launch that could happen is in 2027. But even with this, we could face a 2 to 5 year gap in our polar altimetry capabilities. So this will break our ability to monitor the changing ice thicknesses on the Antarctic ice sheet. And since these are our biggest source of uncertainty in future sea level predictions, these capabilities are of major societal importance. And so there's an urgent need that we address this. The mitigation strategies could include extending the current life of Cryosat-2 and ISAT-2, or accelerating the launch of Crystal. But yes, there is an urgent need that we do something now. The Earth observation data that I've shown today, and that these satellites produce, is really vital for underpinning all climate change science. So I hope I've communicated that to you today. And now I will hand back over to Heather to talk about her work on Getz.
So you're back with me. Hopefully you can stand some more of my voice. Apologies. So we're going to talk about my study that came out this year in the Getz region, and we think it's quite a good example of how using these satellite observations, using the new capabilities of high resolution data and incorporating it with models to see what's going on in this area. There's been a lot of attention in the Amundsen Sea sector, which has Pine Island and Thwaites, the fastest flowing glaciers in Antarctica. And Getz is just around the corner. So this is the Getz ice shelf, and this is a Korean ship in front of it. For context, that's 110 meters long. I think when we're looking at Antarctica, it's quite hard to grasp the scale that you're looking at, even for me who looks at it every day in satellite images. It's over 14 million kilometers in area, which is almost twice the size of Australia. So it's large scales that we're looking at. So it's located in West Antarctica. And as you can see, Pine Island and Thwaites, the fast glaciers, and then Getz is this long stretch just there, which extends 1,000 kilometers further around the coastline. It covers about 10% of the West Antarctic ice sheet, and has like 8 large islands at the front of the shelf, and 23 pinning points. So these points are interacting with the ice shelf, causing buttressing. As such, the carving front is relatively stable. So why are we interested in this area? The majority of it is grounded well below sea level. We see strong thinning from the altimetry record, like Bryony's just said, over the past 25 years on both the ice shelf and the ice sheet. But there remains uncertainty around the physical mechanisms driving this change. In Antarctica, ice losses are dominated by dynamics, so changes in ice flow. That accounts for 98% of Antarctica's loss of ice. And that's where I focus. I look at the speed change of ice. So we do this by using satellite imagery. And on your left, you'll see this animation, and hopefully you can pick out the ocean along the bottom. You can see all the bergy bits floating around the front of sea ice changing. And then you see the bright white floating ice shelf, and then the darker grounded ice sheet behind. Now, I don't think you can pick out by eye, or maybe you have better eyes than me, the movement of the ice sheet in this. But we use algorithms to do this. So we have algorithms that map the difference between two images by identifying features such as crevasses. So this is an image of crevasses on the Antarctic ice sheet taken from a plane. So this is the kind of features that we're looking at. And basically we look at two images, we look at the difference between them, and then we get a displacement for that. Now, I predominantly use Sentinel-1, and we get images every 6 days over the majority of Antarctica, which means we can look basically at a weekly scale of how speed is changing. In this study, we wanted to look at a longer time period, so go back 25 years. So we included ERS-1, this lovely satellite here. But the older satellites has had much less coverage and a much shorter time frame of data available. We also included an existing data set called Measures, and this is an example of one of the beautiful velocity maps we have over the whole of Antarctica. So there are 14 flow units in Getz. You can see the black lines appearing here. 2 of them flow at speeds of over 1 kilometre a year. I think when we think of glaciers, we often think of them moving at a snail's pace at centimetres a year. But in Antarctica, we actually get speeds of up to nearly 4 kilometres at Pine Island. So they're moving relatively fast. This is basically the same image, but rotated. So you'll see these flow units are numbered. 10 to 14 were named based on US expeditions, but 1 to 9 were unnamed until recently. And the thing about Getz is it's so remote. All of Antarctica is remote, but Getz is particularly remote and difficult to get to. And much of it hasn't been stepped on by humans, which means we don't have much in situ data. to further validate our satellite data and also measure things that we can't at much finer detail than we can do using satellites from space. So I'm going to show you an example of one of the glaciers. So this is flow unit 12, which flows in a steep valley onto the ice shelf. What you'll see appearing here is the speed along that black dotted flow line that we saw. And you'll see as it gets lighter, it's moving closer to present in time. And we're seeing the negative numbers, that's the floating ice shelf part, and the positive numbers is the grounded ice sheet. And as you can see, it's increasing through time. So we then looked at this over the whole region, and at the top is a speed change map. So the red areas are where we're seeing this strong speed up signal, and blue areas is slow down. And we look at the grounding line, that transition between the floating ice shelf and the grounded ice sheet. And we look at where the flow lines intersect with the grounding line. And what we found is that basically the mean speed up was around 25% for all the glaciers. But 3 glaciers sped up by over 44%. We then looked at the thinning record, so this altimetry record, and that's the bottom map here, and where the dark red area is where it's thinning strongly, and hopefully you can see that maps on quite closely to where we're seeing the speed change. And that's important because when we couple the thinning with the speed up, it means that we know that this area is in dynamic imbalance, which means it's losing more ice than it gains through things like snowfall. We also found that there was a 50% speed up equated to about 5% thinning. So as I mentioned, we used earlier satellite data of ERS1, and often we can only get coverage of part of the Getz Basin. So to account for this, we included an optimized ice flow model, which sounds complicated, but basically we fed our observations into a model which provided information about the physical properties of ice and how it flows, and the observations helped train the model to predict what it was like during this time period. And we got very close agreement to our observations when we had coverage of both. And the reason for doing this is that meant we could look at the mass balance, which is the balance of what's coming into the ice sheet through snow and what's leaving the ice sheet through melt and calving. And what we found were that 315 gigatons or billion tons have been lost over the last 25 years, which is nearly a millimetre of global sea level from just this one region. We also saw that loss was 4 times greater in the 2010s compared to back in the 90s. So you'll see on this blue line, there's quite a steep drop-off after 2010, and basically there was less snowfall from that period. So we see this accelerated loss. And to put this into a little bit more context, these are ice cubes of what was lost in each of the time periods. So we've got 1994 to 99, then we've got 2000 to 2009, and then 2010 to 2018, and it's over Manhattan for scale. So this is the amount of lost ice that has been lost. And as you can pick out, the most recent decade, we see a lot more loss of ice. And even more context, that amount of ice is the equivalent of 126 million Olympic swimming pools worth of water. We also looked at the ocean characteristics, so we know that the ocean interacts with the ice shelves. We know that the front of the Getz region is relatively stable, but it's still interacting underneath the ice shelf. And we did this by looking at CTD measurements. So there are these purple dots taken here, and that's basically where an instrument is dropped off the side of a ship, and it records things like temperature and salinity as it drops down, so we get this depth profile, which you can see in the graph on the right-hand side. And this blue shaded region is the depth variation of our grounding lines, so where we think our grounding lines in this area. And as you can see, the curve of the line varies through time, and that's the changing thermocline depth. And that's where we're seeing modified circumpolar deep water coming onto the continental shelf, this warmer water coming on, and it varies through time. You'll see here that the red and blue arrows represent what we think the circulation is happening under the ice shelf itself. So we see this warm water, we see the water coming in and then causing some melt, and then melt water leaving. Interestingly, our speed up record shows a linear increase in speed, so we're not seeing the fluctuations that we're seeing in the ocean record, which we have seen elsewhere in places like Pine Island. So we concluded that it's likely that a longer term forcing, probably an ocean forcing, triggered this speed up change that we've seen in this area. So to summarise, in the Getz region, we've seen speed up here, and that's important because it was the first time that it was shown over 1,000 kilometres further around the coastline than we previously reported it. We've seen that the losses are higher in recent years, that there's long-term ocean warming going on. But importantly, we need consistent sampling in time and space of the ocean data. So those purple dots we saw in the last slide, they're the measurements we have, but we don't have them in repeatedly the same spot over time, which would be really useful to see how it's changing. And then also in our speed measurement, so it's really important we continue to measure speed and look at how it's changing. Speed up is often the early warning signal that we can see. We see it happen quite quickly. We've got the 7-day repeats, so we can look at that change going on. And because they're moving so fast, over a kilometre a year, we see the magnitude compared to the thinning rates, which are about in 1 or 2 metres a year. So you can see in the speed record, the larger magnitude means we can identify it earlier on. And this is important because understanding of the speed change and combining this with the thinning and looking at these localized details wasn't always possible. There was field work where you could do occasional measurements, but with the ever-increasing resolution of our satellite data, we are now seeing these detailed changes and being able to look at individual glaciers and how they're changing through time at ever-increasing detail. So I'm going to invite Bryony to come back up. And hopefully the Getz study shows how the combination of satellite data, modelling, and it's still investigating areas that have been less studied is really important in West Antarctica in particular. But now we're going to take you through the glacier naming. So as I said at the start, I put in a proposal to name the 9 unnamed glaciers in our study. I'm a UK scientist, so I went through the UK Antarctic Place Naming Committee. And why would you name a glacier? Well, in the study itself, we had to refer to them as very exciting names such as Flow Unit 1 and Flow Unit 2, which gets mildly confusing when another area without glacier names then calls it Flow Unit 1 and Flow Unit 2. So it's really important we have distinct names for these areas. You might have seen there was quite a lot of news coverage over it, particularly because we named one of the areas Glasgow Glacier, but we will go through that in a bit. And we saw the opportunity in naming these glaciers to honour the climate science community and the policy-making community and the effort that's been put in over the last 4 decades to try and understand the changes in our climate and try and understand how to deal with that those changes. And I think images of melting icebergs and meltwater on ice sheets has become synonymous with climate change, and hopefully by naming some glaciers with these after the location of important climate summits, conferences and reports, it sends a stark reminder of what we are fighting for, or one part of the world that we're fighting for. So we'll start. I hope you don't mind. We're going to go through these glaciers and explain the reasoning behind them. So we start with the Geneva Glacier, which represents the first climate conference back in 1979. And it's where scientists called on governments to foresee and prevent potential changes in the climate that might be adverse to human well-being. For context, that's 42 years ago that they were trying to look into this.
And this honours the first Earth Summit that took place in Rio de Janeiro in Brazil in 1992. And this was the place where the UNFCCC, so the United Nations Framework Convention on Climate Change, was first opened for signatures.
Then we have the Berlin Glacier, which represents the first conference of parties back in 1995. And it marked the uniting of the world to come together to try and tackle climate change, and came together with an agreement on the mandate for future negotiations to reduce carbon emissions beyond the year 2000. And to put this into context, I was also born in 1995 and I looked something like this. So to put that in the human time frame, I'm now 26 at the 26th COP after studying climate change for the best part of a decade.
Yeah, so the 2 years of negotiations that followed COP1 led to the formal adoption of the Kyoto Protocol in COP3 in 1997. And so this is what we've named the next glacier after, the Kyoto Glacier. And this protocol set out the first ever legally binding climate targets for developed countries to reduce their carbon emissions. However, there were quite a few countries that decided not to ratify this protocol, including the USA, who wanted to see evidence of meaningful participation from developing countries as well. And this led to a 7-year delay before the protocol actually came into force. And again, to kind of put some human timescale on it, this is a picture of me in 1997 when I was born. But between the time that the protocol was agreed and it came into force, I was then 7 years old and 3 years into school. So these delays that we're talking about, they're long periods of time. It can be easy to forget that 7 years is a lot can change in 7 years. And Kyoto Glacier was found in Heather's study to have sped up by 59% since 1994. So it's the biggest speed up in this region.
At this point, I'm going to highlight that we just named them chronologically and we don't have favourite glaciers here. The next glacier is Barley Glacier, which was to honour the IPCC's 4th assessment report. And this was around the time that it seemed that climate change came into popular consciousness. The thing about this report is the IPCC stated that there were limitations in the sea level rise budgets because our understanding of the Antarctic and the Greenland ice sheet and how it behaves was still in that time frame where we thought it was over very slow timescales, which we've now proven is not the case, unfortunately. But that did then lead to climate deniers and skeptics jumping on that statement. And it's also this glacier had the second highest speed up in this region.
So next we have the Stockholm Glacier, and this honours the location of the approval session of the 5th IPCC assessment report in 2014 in Stockholm in Sweden. So this report represented the biggest coming together of scientists at the time.
Next, we have the Paris Glacier, which honours the Paris Agreement, which I believe you should have heard quite a lot about at this conference, which was a legally binding treaty aimed to limit global warming to well below 2 degrees, preferably closer to 1 degree on pre-industrial levels. Nearly 200 parties ratified this treaty, and they represented around 55% of the world's greenhouse gas emissions at the time. It's also where nationally determined contributions started, which came into effect in 2020. Interestingly, at the start of COP, if everyone met these nationally determined contributions, we're still on target for about a 2.7 degree amount of warming. However, that's gone down to 2.4 as of a report that came out yesterday. But it's important that in the cryosphere, we know that going above these temperatures, particularly if we get anywhere close to 3 degrees, we see a sharp increase in the amount of sea level contribution from these ice sheets.
And the penultimate glacier that we've named is the Incheon Glacier, and this honours the 2015 meeting of the IPCC in Incheon in South Korea to consider the special report of global warming of 1.5 degrees. So this report kind of highlighted the range of climate impacts that could be avoided if we limit global warming by 2100 to 1.5 degrees as opposed to 2 degrees. And some examples of these impacts that we'd avoid is that with 1.5 degrees of warming, global sea levels by 2100 can be expected to be 10 centimeters lower than if we have a 2 degree warming scenario. In a non-kind of cryosphere context, a 1.5 degrees of warming would also mean that we see 70 to 90% of loss of coral reefs around the world, whereas 2 degrees we'd see over 99% loss of our coral reefs. And in the cryosphere, this is particularly important, where every 10th of a degree really matters in what we can save from global warming.
And finally, we've got through them, well done. We're on to Glasgow Glacier, and I felt it was really important to recognise Glasgow in COP26, as I think it marks an important moment in human history. We know that time is running out, and this glacier is now permanently named Glasgow Glacier. So whether the legacy of the glacier and COP26 is going to be a positive one, where humanity stepped up, we stopped society's reliance on fossil fuels, and we reduced our carbon emissions to try and limit the warming, which then will slow down the rate of sea level rise that we are predicting from the ice sheets, or whether we continue to carry on with the disastrous consequences for a lot of communities around the world. I think hopefully we've highlighted through this section that we've been talking about climate change for quite a while now, a whole lifetime worth of COPs, and it really is now time for the action to start. It's unequivocal that humans cause climate change, but that also means we have some say in what happens next, because we know if we reduce our carbon emissions and have zero carbon emissions, then the warming will slow, the warming should stop, and then so the positive thing is we still have a chance to do this, and it's scientifically possible to limit us at 1.5 degrees, which is the closer we can get to that, the better, because it's less chance that we're crossing important thresholds in our climate system that then mean that we get runaway issues such as the instabilities that we've shown in the Antarctic ice sheet. And this is a slide of early career researchers in the cryosphere, and we put them up here. They study all aspects of the cryosphere. The early career researchers like myself, Bryony, and the early career researchers around the room who are helping support this whole pavilion. And just to say that the decisions that you're making are defining the future of the cryosphere and what we study. And we feel it's important to highlight that diversity is critical at this time. The more different expertise, experiences, and different experiences, the better. It leads to more creative solutions, and it's important to support communities like that, such as Polar Impact and Pride Polar. This is in our region, obviously, because we study the cryosphere. In doing so, we need everyone to try and address this issue.
So the decisions we make here at COP26, they really matter. They matter to us, they matter to many, many generations to come. And we're just going to leave you with some key messages from our talk today. So firstly, that diversity, equality and inclusivity in science and policy, in decision-making, in all aspects of society is really vital if our fight against the climate crisis is to be fair and just globally. We need to ensure continued satellite coverage over the polar regions and all remote regions, because this is what we measure the impacts of climate change against. And alongside this, we do need more in situ measurements of in remote areas to validate the science and also give us information about things that we cannot get from satellites. And finally, we need commitment and action now to net zero and negative carbon emissions, especially when we're dealing with the cryosphere, where we can't negotiate with the melting point of ice. And we'll leave you with this question: what will our legacy be from COP26? And we'll be happy to answer any questions. We've also ordered, I think, some pastries and teas and coffees at the back, so we can have some more informal discussions afterwards if you'd like. We'd love to hear from you. Thank you.
Hello, thank you. I'm Jessie O'Reilly from Indiana University. And I really enjoyed this. Thanks. I'm quite happy to see that glaciers are named after historical moments, as some of the naming traditions in Antarctica have been a little problematic, as some of the folks end up being sort of abusive field expedition leaders and things like that. But this is not what my question is. My question is about satellites. And what are the limitations of this sort of visualization? you noted that it's only every 6 days. I'm wondering if the images are affected by cloud cover or the long Antarctic dark. And then I'm wondering, you noted here and in your talk that more in situ field measurements could be useful. Could you explain in a little more detail the limitations of the remote imagery, and then what the field measurements might inform in your study? Thanks.
Yeah, I can take this question. I'll take this. Yeah. So that's a really, really important question. And we have, in terms of the different measurements that we can get from satellites, we have a whole host of different sensor types. And so to address the cloud cover and the polar darkness, we do have a series of satellites that use radar, which are longer wavelengths that can penetrate the clouds and they don't rely on the presence of the sun to see the surface. And there's been big developments, and we've got so many more satellites like this that can provide us this information. But yeah, if we are looking at optical data, that is a major limitation that can't really be avoided. In terms of the in situ measurements, do you want to touch on that?
Yeah. So satellite data is amazing. As you can see, we can cover the whole Antarctic ice sheet, and we're getting this increasing resolution so we can look at these individual glaciers now. But we also need in situ data so that we can get even higher resolution data and compare it to the satellite data itself. So we have continuous campaigns that have gone on repeatedly over the same place, and we have these in certain areas. There's a lot of areas where we still don't have that. So whilst we're confident that our satellite data agrees where we have the measurements, it's still important to make sure that it's consistent over the whole of Antarctica. There's things that also, so particularly tricky is like understanding bedrock and measuring bedrock. So getting in the field and using the ground penetrating radar can be a really good way to do that. There's also been campaigns such as Operation Icebridge, which is a plane that flies over and uses the radar to measure the bed elevation. The difficulty with the field campaigns is that Antarctica is enormous. It's difficult to access, so it's understandable why it's only in limited accessible spaces that we only have it at the moment. But what I will say is that we're very confident in our satellite observations. This is just to have even more confidence and also improve models of things like snowfall and the changes in snowfall, particularly in the Getz region. There's not really any measurements of that kind to make sure that we're using the best model we can.
Yeah, hi, my name is Charles Archibald. I'm University of London. Past scientific predictions have been underestimates. For example, in Greenland, the Thwaites Glacier, the melt rate was underestimated by scientists. So I'm just curious as to what the range of confidence there is at the moment in terms of the rate of melt, and what is the unlikelihood or likelihood of a 1 meter rise in sea levels by the end of the century, and what is for Britain a major concern is, of course, the change in the ocean currents. Do you have any sense of and that will be affected by the cryosphere, obviously. What is the likelihood of Britain actually entering a new ice age because of what the cryosphere does?
Yeah, cool. So the first part of the question was about how confident we are in the changes going forward and what we're seeing now, because previously we've underestimated things. I think a lot of that underestimation comes from the fact that we didn't know that the ice sheets could change on these kind of shorter timescale, and it's thanks to the satellite revolution that we measured that and seen that it is reacting on this shorter timescale to the amount that we're warming the atmosphere and the warming ocean. So we've got evidence that the rate has increased, the rate of change, the rate that we're losing ice is increasing. And that's important. Going forward, we're pretty confident that as the warming continues, we're still going to see this increasing speed, the increase of ice loss. But as I mentioned in the first part of the talk, there are some big question marks. So there are these instabilities in the ice sheet, the marine ice cliff and the marine ice sheet instability, which, if they're triggered, are a real issue because they are irreversible on human timelines. So we get the runaway. And if you think back to that graph, that red dotted line that went twice as high as the other projections, it's stated in the IPCC as a low likelihood but high impact event. So if this happens, it can be really disastrous because it's twice the amount of sea level rise that we're planning for. So I think it's important that we consider and put effort and money into research investigating this, so we can either say it's happening, it's going to happen, or it's not, but just ignoring it isn't the best course of action. I think there needs to be I think it's sensible to include it in thoughts, because at the moment all of the policy is based on the IPCC scenarios, which are below a metre or so. So we need to consider that there are worst case scenarios out there, and really continue working on it.
And also to address the ocean circulation, I'll take these off to avoid field feedback. To address the ocean circulation question, I think that the timescales over which the ocean circulation kind of system works is over much longer than kind of human timescales. Like some ocean currents don't kind of rise to the surface for hundreds, maybe thousands of years. So the changing circulation patterns caused by increased melt and influx of fresh water is a serious thing that we need to consider, but the timescales are not as pressing as the impact of sea level rise, and the impacts will be global. So the UK isn't just going to see an ice age. If stuff happens like that, it's going to be more of a global impact. And whether it affects the jet stream and the Gulf Stream, the Gulf Stream in the ocean.
Yeah, I would just the importance of West Antarctica and where this water is coming from. It will also depend. So we know Greenland at the moment is outpacing Antarctica in the amount it contributes, but West Antarctica towards the end of the century is probably going to take over. And it's important that we can understand, more detail and more we refine our knowledge of these processes that are happening in Antarctica and how they're changing, the better we're going to be able to predict where the water comes from, and then that interaction with the ocean. If there's no other formal questions, then there are tea, coffee and pastries in the corner, and we're happy to have informal chats and carry on. I think Tom's going to take over.
Yes. So thank you so much, Heather and Bryony. That was really interesting. And as one of the early career scientists that was up there on the picture, I fully support the statement on both the importance of inclusivity and diversity in science, but also the message how much our actions now matter. So this event now comes to a closure, but we have another event at 11:30, which will be on the limits of adaptability. But now, yes, we have the reception as well. Thank you.